In this video, we are going to have a look at type classes, which are a core concept in the Haskell programming language. In fact, type classes are so important that we can find them almost anywhere, and we already had our occasion to look at some use cases of type classes as an example when we talked about the type signature of the plus operator. And in the type signature, we said that the type that matter is everything that is on the right of this big arrow. And we only said that whatever is on the left are some constraint that we put on the type we are using on the type definition. Well, those constraints are type classes, and those type classes, in this case, this num type class, is making sure that this A does have some particular features that may be needed in order to use that type inside, of course, the definition of class in this case. So we know that type classes are a way to define some common properties that some types can have, and in order to define a type class inside a Haskell file, we use the keyword class. And now, if you have experience with object-oriented programming languages, this class keyword has nothing to do with what you're used to. In fact, the class keyword is used in order to create a class of types, which is a different concept that creating some object in object-oriented programming languages. So by using this class, we are telling to GAC in this case that what follows is a class of types declaration, meaning that if we later create some types, we can use this class of types we are defining in order to define the properties that are peculiar of this class of types. And we can see as an example the implementation of the num type class. As we said, num is a type class, and here we see that num is defined with the class keyword, then the num, of course, since this is the name of the type class, and then a generic type, meaning that when we give a type to the num type class, we are defining that type to be member of the num type class. And then we use a where that, as we saw some videos ago, is a keyword that allows us to define a block of definition. And in that block, we do have the common properties that a generic type, which is member of this class of types, must have. And usually you'll also find a line of code similar to this one. This is a pragma, and it is used by the compiler. And in this case, in a type class definition, we have a minimal pragma, which tells the compiler that in order to have a proper instance of the num type class, the minimal function that are required to be implemented are those one. If you find this line, that means that these are the minimal function that you need to have in order to have such a instance of that type class. And if there are any others, then those can be derived starting from those minimal. In any case, let's try to define our own type class. And when defining a type class, you should think at them kind of a virtual class for your types. So for our example, I will define a type class that I'll call person. And here I'm defining a generic type in order to use this generic type in the common properties definition. And in order to open a block for the definitions, as we saw, we have to use the where keyword. And here we can define some common properties that a person should have. As an example, we want a person to have a name property, which will be a function that, given a generic person type, returns a string. And since you can think at type classes kind of a virtual class, we don't have to define an implementation here for this property. And then we may also want, as an example, an age that, given a generic person type, returns an int. Now, if we look at the type definition of those properties, if we want of this type class, we see that by asking the type of name, we get that name is a function that, given a generic person type, returns a string. And notice here how we don't use a capital for generic person type, and this means that this, if it was wrote just like this, could be really any type possible. But here on the left of this big arrow, we have this person followed by the generic person type, meaning that we have put a constraint on this particular type name in this definition that says that generic person type must be, or in other words, must implement the person type class. And we could also find this constraint possibly on functions that are not defined necessarily inside the type class. As an example, I could define a function that I'll call is of legal age, and this is of legal age takes a generic type, and here I called it person, but there could be a generic type as we usually see on types definition of the default Haskell language. In any case, I assume that person is more appropriate here, but this type signature, as it is written here, could take any type. And by any type, I mean we could use here booleans, integers, whatever, really. And this is not something that we want. So we want to constrain this generic type to be an instance of person, and we can do, of course, that by using this syntax right here. We put a constraint for person to be an instance of the person type class, and by using this constraint, we are sure that now person is an instance of this type class, and by just being an instance of this type class, we are sure that person does at the very least implements those two functions. And the reason for why you may find something like this in a type signature is that that particular implementation of the function does use some of the function defined in the type class, and by doing so, this function could work for any instance of the person type class, but would not work, as an example, for a value like an integer, which is not an instance, of course, of the person type class. And to show you this in action, let me define a couple of data types. And here I do have defined a student data type and a chef data type. Those types are aliases in order to understand what the inputs are for, but we are just using string and integers. In any case, in order to make those two data types instances of the person type class, we have to use the instance keyword followed by the type class of which we want to declare an instance of, in this case person, and then the data type that will be an instance of the type class. So we will use student, and after this we will need, of course, to implement these two function for this specific type. So we'll need a declaration block, and in order to do so, we'll use the where keyword, and here we define the name to be something that, given a student, returns is name, and we'll do the same for the age, and then we'll do something similar for the chef. And by doing so, now student and chef are valid instances of the person type class. And by reloading the file so that we have the new declaration available, I can show you that is of legal age function now works with both the student data type and the chef data type being both valid instances of the person type class as we define them here, but the is of legal age function does not work with, say, things like numbers, and we see that we get an error telling us that, of course, it cannot find any instance of the person type class for this particular value. Well, of course, we could define, if we want, an instance of the person type class for the int, even if it doesn't really make any sense, but still we can do that. And if we now reload the file and try to ask if 18 as a number is of legal age, well, of course, specifying that this is an int since we only defined the type class for ints. Well, if we now provide 18, of course, 18 is valid, but if we now provide 17, 17 is less than 18. So, of course, making an instance for the int type of a person type class doesn't really make any sense, but still, we could do this if we want. And since the is of legal age only checks that the types given as an instance, and of course it checks that in order to use this function, which is defined for the person instances, well, in this case this function just works since we defined previously how to let that function work. In any case, this is how you could define your own type classes in Haskell. Of course, this is just an example of type class. So we saw how to define them using the class keyword. We saw how to use them inside other function and why we would have to use them. We saw how to declare instances of type classes for the data types that we are interested in, and we'll use this concept in the following videos. So if you are not subscribed, I suggest you to hit the subscribe button right now. In any case, I want to thank you for your time. Remember to stay decentralized, and I will see you in another video. Bye bye.